Okay, now we're going to move forward and we're going to apply Snell's law. But this time we're going to be looking at not a single surface, we're going to look at a parallel-sided block. And we're going to calculate the total deviation from surface 1 to surface 2. So my calculations for surface 1 will be on this side, calculations for surface 2 will be on the other. So let's move forward then and decide what is actually the total deviation of the ray of light that is originating in air. And if you're not told anything, you're to assume that the refractive index material that surrounds that parallel-sided block is air, unless told otherwise. So we have an angle of incidence coming in with an equal angle of reflection, which is demonstrated by this diagram, which is not to scale. So again, let's use Snell's law and calculate what is the angle of refraction at surface 1, what is the angle of deviation at surface 1, and then we need to carry on through the parallel-sided block, and we need to exit out at surface 2 back into air. So starting off surface 1, we identify the formula, which is Snell's law. First N stands for the refractive index that the light ray is originating in, which in this case is air. Sine, the trig function, and whoops, I forgot my I in there. Okay, so N sine I, 1 sine of 20 degrees, is equal to N primed, which stands for the refractive index of the media inside the parallel-sided block, which in this case is crown glass, which is equal to 1.523 sine I primed. So we're exactly where we were when we had the single example of Snell's law. So the first thing we have to do is sine of 20 times the refractive index, which is equal to 0.342020143. Again, you must keep all your decimal places in there, equaling 1.523 sine I primed. Now we don't want 1.523 here, so we divide this side of the equation by 1.523, which means we must do the same function on the other side, which gives me then 0.224570022 equaling sine I primed. As our first example, divide this side by sine, divide this side by sine, which in my calculator is second function sine, which gives me 12.98 degrees to 2 decimal places, equaling I primed, or the angle of refraction at the first surface of my parallel-sided block. Now, as mentioned before, as an optician, I don't work in 12.98. You will round this to the nearest degree. And talking about rounding, if this was 12.5, I round up. So 12.4, I would have rounded down. So that's how I round in any of the equations that I'm looking at. So I primed is equal to the nearest degree, which would be 13. So now I have to look at the diagram, make sure it makes sense. I am still going from less to more dense, which means the angle of refraction at the first surface has to be less than the angle of incidence. This is not to scale. What I end up having then is an angle of refraction between the normal and the refracted ray equal to 13 degrees, and it makes logical sense because light's traveling from less to more dense. Now, as you can see, there's also going to be some deviation that's going to occur. Deviation always occurs when refraction takes place. So, if you were to place a ruler on here and draw a straight line, between the refracted ray and this line would be the angle of deviation that occurs at the first surface. And if you do need a formula for that, it would be the angle of incidence at the surface subtract the angle of refraction at the surface would be equal to deviation at the surface. And I'm just calling this deviation 1. Not to confuse anyone, because I am dealing with a parallel-sided block, which means I have more than one surface. And obviously, when I get to the end and calculate the total deviation, it's going to be the sum of D1 plus D2. So we have 20 subtract 13, which would be equal to 7 degrees. So the deviation that occurs at surface 1 is 7 degrees. Now typically, if we're just doing one surface, we stop there. But because it's a parallel-sided block, we have to continue with the ray through the crown glass parallel-sided block until it strikes the boundary between two media again. So with a ruler, if this was to scale, you would carry on this line until it strikes the boundary between two media. And it's at that point where the incident ray strikes that boundary that you put in another normal. So between this ray, which has now become the incident ray, and the normal, you're going to have an angle of incidence of 13 degrees. The reason why it's an angle of incidence of 13 degrees is because it is a parallel-sided block. This angle is always equal to this angle. Later on, we're going to look at a prism being a non-parallel-sided block, and you're not going to have the same kind of relationship occur. So as I know this is the angle of incidence, and I know that I'm inside crown glass, I now have to calculate what is the angle of refraction, or the angle of emergence at the second surface. And because I'm going this time from crown glass, which is 1.523, into air, obviously this time the refracted angle at this surface is going to be greater than the angle of incidence. So we got to go back to Snell's law again at surface 2 and calculate what is the angle of refraction at surface 2. So n sine I equals n primed sine I primed. So exactly the same formula, calculating and working it out the same way. Where an error usually occurs, if you're going to make one, is you forget. You are inside the parallel-sided block made out of crown glass. So the first n stands for where you are, which is the 1.523. Then obviously sine, and we know that it's 13 degrees because it is a parallel-sided block. Sine of 13 equals, the n prime this time is you're going back out into air, so it's 1 sine I primed. So we have to calculate what is the sine of 13, and then we have to multiply it by the refractive index 1.523. So 13 sine times, and it comes out to be 0.342600,456 equaling 1 sine I primed. Again, don't forget what we're doing. We're trying to calculate the angle of refraction at the second surface, and it's going to be interesting because if you're kind of following the pattern here, and it's a parallel-sided block, what we should be calculating and what we should be getting at as an answer is 20 degrees, because what came into the parallel-sided block should be the same angle of emergence into the less dense medium. So divide this side by 1, divide this side by 1, you're going to have the same thing. Then you're going to divide this side by sine, so you divide that side by sine, which is second function sine. And we get 20.04, which is 2 decimal places, equaling I primed. Again, I don't work that way. To the nearest degree, I primed is equal to 20 degrees. Now, this shouldn't be a surprise because on a parallel-sided block, as previously mentioned, this is exactly what happens. So, if I were to come over here and I was drawing this, and it would be to scale, obviously, the refracted ray would go in that direction. The angle of refraction between the normal and the ray is equal to 20, and it should be a lot larger than what went in because you're going from dense into less dense. So what you're seeing is very unique and very different and does occur only on a parallel-sided block. Now, we still have to calculate the angle of deviation. If you need a formula for that, I always tell students it's a big angle, subtract a little angle, because we don't work in negative angles. So if you needed a formula, this time at this surface, it would be I prime subtract the angle of incidence would be equal to D2. So that would be 20 degrees subtract 13 degrees is equal to D2. D2 would be equal to 007. So it's unique. It's different than a prism. And a prism we're going to look at shortly. We're not done, because when you have more than one surface where refraction occurs, or you have multi-refractive media, such as your eye, light rays would go through the cornea, then it would go through the aqueous, then the crystalline lens. So you have multiple refractive media that the light has to pass through and refract through. So deviation will occur at every single boundary. So total deviation would be equal to D1 plus D2, which is equal to 007 plus 007, which is equal to 14 degrees. So the total deviation on this particular parallel-sided block is 14 degrees.